Yeah, just hold on for a moment. Just I'll let you know. Hello, hello.
Yes, sir.
Yeah, somebody had a question. Yeah, please ask. What is the question?
Sir, I was just asking about the midterm syllabus.
Yeah, so as I told, midterm syllabus will be up to the point we discussed in the class just before the midterm. So it is, and it is generally this way for all the courses. Generally, in IIT, uh, everything that is covered before midterm is the syllabus for the midterm.
Okay, sir.
Excuse me, sir.
So yeah,
Sir, how can we have 7 exam in 4 days?
no, you will get used to it. It is, it's not. It looks difficult in the beginning. You know, I had 7 exams in 2 days, actually midterm exams in my first year. Okay, so it is better to prepare beforehand actually. So that way you are well prepared for the midterm exams.
Sir, will there be
Don't
class
leave
or
your
no
preparation
class
for the
during MTE?
exam day.
Sir, will there be class or no class during MTE?
And Dikshant, I would recommend you to talk to TAs about your problem of your course project. You were mentioning that you wanted a selective current in a part of your circuit. You know?
Yes, sir.
So just talk to the TAs at least. You can keep in touch with the TAs, and they would should be able to help you out in that.
Sir, like I found a way that now it seems like it can work.
Okay, using BJT or something
Yeah,
else.
BJT only, sir. Sir,
Okay,
I
okay,
put
yeah,
the whole
that
cube in parallel with the BJT.
okay, okay. Yeah, let's see how you come
Yes,
up
sir.
with the result. So let's maybe begin our discussion, and this is what we have been discussing in our class, and I think it is taking quite a time to discuss, but I guess it is worth spending the time because no point in leaving things unclear. So this is the theory of PN junction, the diode, which is I would say one of the most fundamental devices, electronic devices, solid state electronic devices, and Uh, although this looks very simple, but the physics of diode uh, is quite involved, I would say, and it is better understood if we understand the band diagrams of the semiconductors and band diagram of the entire device. Okay, and here the notion of Fermi level is also important, and Fermi level in a way tells us about uh, the energy of the charge carriers in a system. Okay. And in a PN junction in equilibrium, this picture is the PN junction in equilibrium. Um, there is a diffusion of holes from P side to N side, and equal amount of hole drift is there from N side to P side. And similarly, there is electron diffusion from N side to P side because a lot of electrons are there on N side, and lot of and very less number of electrons are there on the P side. And equal amount of opposite electron drift is there from P side to N side, and that's how the equilibrium is maintained. each process is being balanced by a reverse process of exactly same order, same amount actually, same. So this is the no bias condition. The equilibrium condition is the no bias condition. In reverse bias, the depletion region is increased and the diffusion current, the majority current is diminished. So the majority current approaches zero and the only current that is left in the system is the minority current. And this current is very small order. The order of this current is very small. It is few. It typically is in microamperes. It could be anywhere from few nanoamperes to microamperes actually. Okay, and then in forward bias, the reverse happens. In forward bias, the depletion region is the width of the depletion region is reduced, uh, and the majority current is enhanced. And the reason for that is that this barrier that we can see in the band diagram is reduced, and so there are a lot of electrons that are there on the n side. They can now go to the p side by diffusion process, and that's how the majority carrier current is increased in the forward bias. Okay, there is an
Sir,
important point. Yes, yeah.
sir, if we apply positive voltage on ECP, then it increases, sir. Then bandwidth increases, sir.
Positive voltage on ECP.
Bandwidth increases, sir. Then,
Bandwidth. Sorry, what do you mean by bandwidth here?
sir, V naught Q.
No, it does not
Depletion.
increase, because if you are applying positive voltage on p side, then it reduces the depletion region.
It should increase, sir. Positive and P. P means holes. Positive charge, positive voltage.
Yeah, so if we apply positive voltage on this side, these levels will go down. ECP and EVP will go down, and this barrier will be reduced. This V naught will also be reduced. This barrier potential or the junction potential will also be reduced.
It should increase, sir. ECP V is positive and holes charge is positive. So potential energy should increase, sir. V into Q.
No, it is for the electrons. The energy that is shown here is for the electrons actually. Just for a moment. Yeah, so the point here is that this band diagram is drawn for the electrons. So these ECP, ECN, EVN, EVP, all these are for electrons. Okay. So when we apply a positive voltage on ECP, it means that this ECP will also go down and this V naught will reduce. This barrier will reduce and the depletion region will also be reduced.
Okay, sir.
Okay, so this is how it is, and uh, this is a more, I would say, cleaner picture of uh, forward bias, equilibrium, and reverse bias. And as you can see that the electric field in the junction is shown with this arrow, and the length of the arrow is actually exactly proportional to the amount of electric field. So yeah, one thing that I was going to tell you here is that this minority carrier current, this IS, this is there both in forward bias and in reverse bias. Although it changes, the magnitude changes, but it does not change a lot. The reason is that the depletion region is not completely gone even in forward bias. And as long as this depletion region is there, then the minority carriers quite close to the depletion region can be attracted by the electric field and can be taken away to the other side. And that's how this IS is there. That's how this IS is actually created in the device. And this IS is fairly independent of the applied reverse bias. Although it depends, we'll see that a little bit later, but it is fairly independent of the applied voltage. And but on the other hand, this majority carrier current, this diffusion current, it changes. Okay, so it may be there. Uh, for example, in forward bias case, it is there. The value of the majority carrier current or the diffusion current is increased drastically, and in reverse bias case, it is reduced or it almost becomes zero. Okay, so so this is the case for equilibrium, forward bias, and reverse bias, and these are the depletion regions. The polarity of applied, externally applied voltage VF is also there. As you can see that in forward bias, positive voltage of the battery is connected to the P type semiconductor. And opposite is true in the case of reverse bias, where the negative terminal of the battery is connected to the P side of the semiconductor. Okay. So, and this is the picture of carrier flow in equilibrium and in forward bias and in reverse bias. In forward and reverse bias, we are assuming that a steady state is achieved, which means that the flow is not changing. It is a steady state. Now a constant voltage is being applied at the battery terminals, and that is essentially uh, reducing or increasing the depletion region in case of forward and reverse bias. So as you can see that in equilibrium, the diffusion and drift currents are exactly opposite in magnitude, exactly same in magnitude and opposite in direction. In forward bias, the diffusion current magnitude is more. The diffusion current is essentially this this black arrows, and the drift current is these light blue arrows. So in forward bias, this diffusion current magnitude is increased. The reverse bias or the drift current magnitude is almost the same. In reverse bias, the diffusion current magnitude is reduced almost zero, and the reverse bias, or sorry, the reverse current or the drift current magnitude is almost the same. And with this, taking everything into account, the diode current can be written as or given by this expression. ID, the diode current, is equal to IS, means saturation current. This IS is the reverse saturation current. It just means the minority carrier current, or the current that is there only the current that is there in the reverse bias uh, into exponential Vd by nVt minus 1. Where we discussed a little bit about various parameters involved. N is the ideality factor, Vt is the thermal voltage, Vd is the applied voltage on the diode. Here it is shown by Vf, but it is actually Vd. It's just a matter of convention. Sometimes it is in forward bias, it is written as Vf, forward bias voltage. In reverse bias, it can be written as Vr, the reverse bias voltage. Okay. There is another point that I would like you to remember actually, and you would do it, you would also derive it mathematically once you do it rigorously. And I highlighted this in the last class as well, that the concentration of majority carriers and minority carriers in a material is actually related to each other. So if the majority carriers is more, for example, if the Fermi level EFN is closer to ECN, it will be farther away from EVN and the minority carrier will be less. Similar is true for the p-type material. So this Diffusion current is the majority carrier current, the drift current is the minority carrier current. So their magnitude is also related to each other. And that's why this first term on the right hand side of the current expression, this term also has IS factor in it. Because the forward bias, the diffusion current is also related to the saturation or the reverse current in the system. Okay. So at the moment, I would just like you to remember this. And qualitatively, it is clear from the band diagrams. But you will also do it more rigorously later on. Okay. Any question up to this point?
Sir,
Yes.
sir, as you said that when the majority carriers are more, the minority carriers are less. But from the formula of ID, it is showing that when IS is more, ID is also more.
Yes.
Sir,
Actually,
isn't it contradicting?
no. I get your point, but uh, I just this IS is almost constant for a system. Okay. As you can also see from these diagrams that this IS in all three cases, these arrows, these light blue arrows, these are almost the same. So IS does not change. It's almost the same.
Sir, even the concentration changes then also.
No, so
Means
if the concentration, yeah, if the concentration changes, IS will change, definitely will change. Um, but the point here is that the relation between the minority and majority carriers in the current, this voltage VD, exponential VD, this factor is more important here. What you are saying is that if there are less number of minority, IS will be less and this uh, forward current will also be less. That's your point, I guess.
yes, sir.
Yeah. So first of all, this the current is related to the carrier concentration, but it is not solely dependent on the carrier concentration. It is the current, as we know, uh, is the number of carriers crossing the junction per unit time. Okay. So if there is more carrier concentration, we can expect that the current would be more, but it is not necessary that the current is going to be more. The current depends on the rate of carriers crossing the junction. Okay.
Oh,
So that rate is related to the IS value and VD, VD value. So if VD is slightly increased, and I would say that this VD factor is even more important. If this VD is slightly increased, this exponent will increase, and which means this exponential will increase a lot, and this current will be increased. So yeah, I get your point that less number of carriers indicate that less minority carrier current will be there, and here from the expression it seems that the majority carrier current will also be less. So that is true. That is true. Actually, I'm not denying that. I am just trying to. I was just trying to tell you that both are related to each other. The carrier concentration is related to each other, and that's why this correlation comes in the current as well. But current is not dependent on carrier concentration only. Current is actually the number of carriers crossing the junction, carrier per unit time. Okay, and that's slightly different than the concentration. That's why this direct implication is not there in this case. Is it clear?
okay.
Sort of.
Yes, sir.
So this is the plot of this is the IV characteristics of the diode, and This you might have seen at many places before as well. And as you can see that this is the y-axis, this is the zero voltage axis as well. Zero voltage means that it is the equilibrium, current is also zero. On the right hand side of the y-axis, on the y-axis we have ID, diode current, on the x-axis we have VD. On the right hand side of the y-axis, it is the positive voltage regime, the forward bias regime of the diode. On the left hand side, it is the negative voltage regime, which means the reverse bias regime of the diode. So in forward bias, as we can expect from this expression, and I had asked you to do a small calculation of Vt, which is the thermal voltage. And what is the value of Vt? It is 26 millivolt. And if the uh, ideality factor is, let's say it is 1, then in this exponent on the right hand side, in the denominator, we have 26 millivolt. So if Vd is slightly above 26 millivolt, then this exponent, this Vd by nVt becomes more than 1. And this value, this current starts becoming positive, so to say. So for few millivolts, for maybe 50, 30, 50 millivolts, there is a positive current in the diode. And initially, this current increases slowly, like any exponential. But as soon as this reaches 0.4, 0.5, then this exponent is also now significant, because 0.4 volts, if Vd is 0.4 volts, it means it is 400 millivolts, and 400 divided by 26, it is around 16, 15, 16 or something around that. So, so exponential to the power 15 is now a good number. So this Is is in microamperes, okay? And this exponent e to the power 15 or so makes this in milliamperes now. So the current starts becoming quite significant above 0.4, 0.5. And for silicon at 0.6 or 0.7, the current is quite large actually. And what happens when the current is very large? So for example, if we are trying to increase the voltage across the diode, and current is increasing a lot, what happens to the battery that is connected to the diode?
So it gets heated and it gets short circuited.
Yeah, it gets heated by why, but why is it heated and why is it short circuited?
So due to internal resistance.
Yes, sir. When current increases, then heat produced also increases.
Yes, so yeah, large current means that the battery needs to supply a lot of electrons, or a lot of ions need to move, and that means a lot of scattering. Electrons will scatter a lot. That will produce a heat. Apart from that, if we manage heat as well, beyond a point, the battery cannot supply a current actually. There is always a current rating on the battery, because there are finite number of charge carriers in a battery, and if even at a small voltage, a circuit is drawing a lot of current, the battery cannot increase the voltage beyond that point. Actually, do you see that? Do you get it?
Yes, you may
That
say.
if, yeah,
Sir, is it true that battery provides electrons, or just it provides the voltage and then current electrons in the wires starts flowing?
no, the electron movement is pretty much there in the battery as well. The battery also provides the ions, although the same number of ions are also received by the battery. Exactly.
So why the limit if it is receiving also electrons?
Yeah, so the thing is that in the battery, there is this chemical reaction that needs to take place, that electrons need to uh, or this electrolyte is there which need to ionize, and uh, beyond a point. So for example, if very heavy current is getting drawn, it means lot of carriers per unit time is required, and that sometimes become for large currents, that becomes the rate that the this battery can supply the electrons. So this there is this rate of this chemical reaction inside the battery, uh, and if there is a mismatch, so what I'm saying is, if there is a mismatch between the two, then it becomes difficult for the battery to sustain the current in the external circuitry. Although nowadays there are batteries, there are big batteries, and we can by using big and more robust and small. But small means small in size, as we have in our mobile phones as well. That the ions reaction time is not so much, because in large batteries the ions reaction time is more. So in nowadays we have good amount big batteries. So this problem can be circumvented to an extent. Uh, but the thing is that as soon as this uh, voltage is around 0.7 or slightly higher than 0.7, then what happens is this in this band diagram, this V naught is also 0.7. It means that now this band diagram is totally flat. And what that means is that there is a large number of electrons here and large number of empty states here, electronic states. So huge current, many milliamperes, and this diode actually burns out if we try to sustain that much current in this system.
So can you please repeat how the band became flat?
So this V naught is there, this QV naught, and this is also exactly equal to the barrier height in the band diagram. Okay. In forward bias means that a positive voltage, either a positive voltage is applied on the P terminal or a negative voltage is applied on the N terminal, or both. If the externally applied voltage is exactly equal to this V naught, what happens is that it shifts the bands to by V naught, because if we apply, for example, if we apply negative voltage here, it will increase the electrons potential energy and this band will come up. And in that case, so for a positive voltage, this band, this ECN will be like this, and this EVN will be like this, and the Fermi level will be something like this. Okay, and if the externally applied voltage is around V naught value, is exactly equal to V naught, in that case, this band is almost flat. So this ECP and ECN is like this, EVP is this, and now this is the new EVN, this red one. This Fermi level is now tilted actually. So Fermi level is now like something like this. Actually, in steady state, there are two Fermi levels in the system, and those are known as the quasi-Fermi level. So one Fermi level is like this, and second is like this. But let's not go into those details, because the Fermi level is an equilibrium concept, and in steady state, which means we are not in equilibrium, we need to use quasi-Fermi levels. Okay, so when the bands are almost flat, and uh, please remember that this is the N-type material, so there are a lot of electrons here. There are a lot of vacancies here, lot of available states here. So these electrons can now directly go here. And if a lot of electrons can move in the diode, they will scatter, they will collide, and the diode may burn out. Ultimately, the point is because of the external limitation of the battery, or as you pointed out that it can be actually circumvented nowadays. Yes, now we have better batteries. So even if we have an ideal battery which can supply infinite amount of current, even then, once the bands are almost flat, in that case, there is so huge current in the diode that the heat is so much that it actually burns out. It breaks the bonds, or it creates a lot of electrons and holes in the system, and it's a burnout situation. So that's why uh, this voltage in a way cannot be increased beyond this point. So, or even maybe after this point, this voltage cannot be increased. Okay, is it clear now, the forward bias situation?
The diode burns out due to excessive heat generated in the diode.
Yes, yeah, exactly. Anything else? Any clarification in this?
So what is VT?
Vt is the thermal voltage, Kt by Q. K is the Boltzmann constant, T is the temperature, and
Okay.
Q is the electron charge. So let's see what happens in the reverse bias. The forward bias is, I guess, more or less clear. The forward bias is governed by the first term on the right hand side, this term basically. In reverse bias, this Vd is negative, and this exponential negative is a very small
Sir,
number.
one thing
So
I
this,
want to ask, sir, of forward bias only.
yes, please.
Sir, like VD, as you said that at point 7 it will be a breakdown, so maximum current will flow for like silicon.
Yes, around 0.7 volts.
So, sir,
It's not.
if yes,
Yes, yeah, yeah. Please,
so
please
sir,
ask your question.
yes, sir. So if the voltage, if VD is zero point 0.6, sir, then it also makes no sense because zero point 0.6 and zero point 0.7, and if denominator is VT like very less, it's 26 milli. It's very less quantity. So zero point 0.6 and zero point 0.7 will be approximately same for that value of VT.
No, but what are you trying to say here?
So like at zero point 0.7 we have the breakdown. So sir, zero point
Uh,
0.6 is also of that caliber only because in the
yeah, yeah. No, I
denominator.
get your point. Yeah. So the point actually, the value, this value of zero point 0.7 comes from here. Uh, Generally, you might be aware that this contact potential for silicon diode, this V naught value, this V naught is 0.7 volts, around 0.67 or something, or it's 0.7 almost. Okay. So generally that value is taken as the reference value. Although you are right that even at 0.6 volts, there is huge current, and uh, but there is another factor here as well. The factor is that in forward bias, let's say if we apply 0.6 volts, then a small amount of voltage is dropped in this region as well. Sorry, let me put the pointer there. Small amount of voltage is dissipated here as well in this quasi-neutral region. Maximum voltage is dropped at the depletion region, but a very small amount of voltage is dropped in these regions because these act like resistors, this region. So if we apply 0.6, the voltage that appears at the junction is around 0.55, let's say, or 0.5 maybe. Okay, so yeah, but this value of 0.7 is taken from this value of V naught actually. Because V naught, the built-in potential in equilibrium for silicon diode is around 0.7 volts. And if we apply, and that's why we take that if we apply 0.7, which means that if 0.7 appears at the depletion region, then these bands will be flat and it's an extremely heavy current. But as you said, there is no clear-cut boundary actually. It's a gradual thing, and even at 0.6 volts, the current is already high. So yeah, the situation is not very different.
Okay, sir, got it.
Yes, so in the reverse bias, this first part, this VD is negative, so exponential is almost zero. And the only component left is minus IS. And very soon, very quickly, this minus IS is achieved in the reverse bias, and it stays like that. And this, I guess, I discussed in the beginning as well, that if we apply a reverse bias, this part of the bands will go down. And there will be a situation in which this is so down that now this ECN and EVP are almost, so this ECN is like here, this way. So there are a lot of electrons here, and some holes are there here because this is a p-type material, holes are here. Okay, so now these electrons can tunnel to this side. Do you see this? I'm sorry, I'm not able to draw it very neatly, but I think I hope this is, at least this is clear. If it is not clear, let me know. I can repeat it again. Is it all right? Is it?
Yes, sir, it's all right.
So this thing that up to this point, when they are not aligned, the current is only IS. The current is a very small current. But as soon as they are aligned with each other, aligned means EVP and ECN are facing each other, and electrons can tunnel from this side to this side. This is known as the Zener breakdown regime. Because the current is suddenly increased, because now a lot of electrons can jump from the N side to the P side. And this is known as the Zener breakdown regime. Okay, because at that voltage, at a voltage when the bands are aligned, suddenly there are a lot of carriers in the junction. This is the Zener breakdown. Although if we reduce the voltage, if we bring the voltage here, again the current will be less. Okay, so this is a reversible breakdown, so to say. And depending on the material and on the doping, this Zener breakdown voltage is different for different diodes.
Sir, what happens to the depletion layer during Zener breakdown?
Depletion layer is actually increased. Depletion layer keeps on increasing.
So there is massive current. Still there is a accumulation of electric field in opposite direction.
Yes, exactly. And this current is not neither drift current nor diffusion current. It is a tunneling current. Actually.
Okay.
And we need to keep in mind that this current is because this current will be there only if the depletion region is or this distance between ECN and EVP is not too much actually, because you might have studied or you would study in quantum mechanics that tunneling current is heavily dependent on this barrier width. If this barrier is large, then the tunneling current is extremely small. So only for few nanometers barrier, the significant tunneling current is there.
Okay, sir.
So if everything is all right, if everything is, for example, if this barrier is of appropriate width and uh, things are not bad, then we will have a Zener breakdown regime in the diode. And this is the IV characteristics in the Zener breakdown. The current suddenly increases at a constant voltage. But there is, this is not, so the term breakdown actually has negative connotations. It means negatively, sort of, that something is breaking down. But it is not that kind of breakdown. If we reduce the voltage, then the diode is intact, diode is working properly, and the current is again IS, minus IS. Okay?
Excuse me, sir.
Yes.
Sir, if we keep on increasing negative voltage VD, then why is this Zener current is negative current is increasing? Because if we are increasing, then the depletion region width is also then increasing. So the tunneling current will also decrease. So why then ID is still increasing?
Yeah, so as I told you that this Zener breakdown is only there when this distance, this width is not so much. And this depletion width and the barrier width are related, but they are not exactly the same actually. Okay, so the depletion region can be up to this point, but this ECN is
Sir, please
up to
turn on
here.
your pointer, please.
Yeah, sorry. So this depletion region can be up to this point, and this ECN or electrons are available up to this point. And in many diodes, actually, in the diodes where the diodes are bigger, this Zener breakdown regime may not be there actually, because the tunneling may not be significant. And in those cases, if we keep on increasing negative voltage, we have something known as the avalanche breakdown. And that is actually, that was the case, that was the kind of breakdown that used to be there in earlier diodes, classical diodes. So yeah, Dikshant, now is your question answered, or can you repeat your question again?
Yes, sir, it is answered.
Yeah, so this in some diodes it may not be there actually, because if the tunneling is not there, it is not there. And in modern diodes, the small diodes, it is always there. Okay, but if we make a bigger diode uh, where this depletion width is in uh, let's say in millimeters or tens of micrometers, then this Zener breakdown is not there. And in that case, what happens is we keep on increasing the voltage, and at a certain voltage, the electric field is so high in the junction, this E is so high that the kinetic energy of the electrons that are crossing, that are drifting through the depletion is so high that they will now further create more electrons and holes.
Excuse me, sir. Sir, can you
Yes.
please repeat what is depletion width and what is barrier width?
Yeah. So again, that is a qualitative sort of explanation that I gave to you. The depletion width is typically depletion width is generally this width that is shown here. And in band diagram, if
Sir,
we
can you
look, just
please
look,
turn on the pointer?
yeah. So in the band diagram, typically this is the depletion width between these 2 points. If we keep on increasing the reverse bias, these bands will go down. Okay. In that case, what happens is, let me erase this. So for high reverse bias, what can happen is that this ECN is now here and EVN is also quite low. So the depletion width might be this width. Okay. But the electrons here might tunnel to holes here. Okay. So the tunneling width is only this one.
Okay, sir.
Although they are not exactly the same, but they are related to each other. So if we have a big diode where the depletion width is big, in that case, this tunneling will also be big, but they're not exactly the same. That was my point actually. Yes, there was one more question, I guess.
Sir, if tunneling width is more, then the tunneling current will be less.
Tunneling width is, yeah, yes, exactly.
Okay, sir.
Tunneling width, tunneling current is highly sensitive to the barrier width, this tunneling width, so called. Okay, and I guess this, if once you do your classical physics course, this quantum mechanics course, you will see in the derivation of tunneling current that this is extremely sensitive to the barrier width and inversely proportional to that. If the barrier is high, the tunneling current is almost zero. So for in larger diodes where this barrier width is more, this tunneling is not there. But in smaller diodes, the diodes that are used nowadays in nowadays transistors, this tunneling is pretty much there. Okay. And
Sir,
actually this, yes, this tunneling is used in applications as well. But yeah, let me take your question first. Yeah, what is your question?
why that diode burnout thing is not happening in this case when there is high current in the Zener breakdown?
Yes, so first of all, that this high current, this Zener current is not so great actually. It is limited by the number of available states here. Okay, number of, let me turn on the pointer. So it is limited by the number of available vacant states here. So these states are not so much, then this current is not so great. Although it is very large as compared to IS, but it is not in amperes. However, this avalanche current, avalanche breakdown, which happens at even at larger voltages, when the carriers have um, so much energy because of this high electric field. Now the carriers have so much velocity, so much kinetic energy that they can break bonds. Then this thing can happen. This avalanche breakdown can happen, and in that case, that burnout thing can take place actually. So this Zener thing typically does not, or Zener thing generally does not break down or burn out the diode. The avalanche breakdown does that. So this Zener breakdown, that's why it is known as the reversible breakdown.
Sir,
Okay, sir.
Yeah.
how can we say whether the tunneling width is large or small?
How can?
And is forward bias or reverse bias tunneling width is increasing or decreasing? About tunneling width.
No, so first of all, that once we make a diode, once we have a diode, that is clear from the band diagrams that how far this EVN and EVP and ECN are placed to each other. And that also depends on the depletion region. It is not that they are completely independent. They depend on each other. Okay. And in forward bias, anyway, this is going up, ECN is going up, so they are not going to be aligned. So tunneling is not there in any case. Tunneling is out of the question. But in reverse bias, at some voltage, it might happen that this ECN is slightly below than EVP. And in that case, this tunneling might take place. Given that this width is not so high. So if this barrier width is conducive, barrier width is not so much, in that case, this tunneling current or tunneling may take place. Okay.
Sir,
Yes.
sir,
Yeah.
sir, can you please confirm that the depletion width is the slant length of the this band?
This length, that's what you're saying.
Yes.
Yeah, this is almost, yeah, exactly that. But
Yes, sir. I mean, approximately, not exactly.
yeah, actually, this is also not so. So this band is generally like this. It's a very gradual change, I would say. Depends on the doping as. Yeah, but it is, as you are right, that it is uh, generally taken to be this distance, this slant length, as you said. But what may happen is that if this comes down, some electrons here might also tunnel. So this tunneling width or tunneling barrier width might be somewhat lesser than the depletion width. Okay.
Sir, I'm not getting what is the tunneling width. Can you please?
Yeah. Yeah. Actually, this is. I would say this is not so important. But let me again try to explain this. That this comes down. This band will come down, and the electrons. So there are a lot of electrons here.
Yes, sir.
You get it. Okay. Now these electrons are sitting, and there are a lot of holes here, which means vacancies here. So if
Yes, sir.
they face each other, these vacancies and electrons face each other, in that case, there might be a possibility of tunneling. Given that the distance between the electrons, the filled states and the empty states is not above tens of nanometers. If it is within tens of nanometers, then there might be a tunneling current. Okay.
Sir, in the diagram, what is the tunneling width? I
Tunneling width is the distance between the vacancies and the electrons, which means
so you mean EVP and ECN?
yes, it is between EVP and ECN, or between the whole states in EVP and electron states in ECN.
Okay,
That's
sir.
what it is. Okay.
Sir, depletion width and tunnel width are same or different?
As I told you that they are closely related, but they may not be same. And the reason for that is that this depletion is also not so sharp. It is a gradual depletion actually. So, so generally, as I told you that depletion is taken to be up to this point, but tunneling might be slightly lesser than the depletion because some electrons might be here and some holes might be here and they might have a tunneling. Do you see this, or this point is not clear? Although this point is not so, uh, I did not intend to bring that point. Is this point clear or not?
Yes, sir. It's
No, sir.
Yeah, so the point here was that if we apply a reverse bias, the situation might be something like this. This ECN has come down. Similarly, this EVN will also come down. Okay. Typically, this depletion width is defined to be this width, the distance between these lines. Do you see this? But what I'm saying is that even in the depletion region, there might be some electronic states and there might be some hole states where this tunneling can take place. So this tunneling distance might be slightly lesser than the depletion region. Although for simplicity, generally we take both of them to be the same. But if we do a more proper and rigorous analysis, they might be a bit different. Okay, is it clear now? Although
Yes, sir.
I must say that this is not so important. This is a very nuanced point. Uh, uh, this is not so sort of, we should not get stuck here otherwise. But if, yeah, if you have a genuine doubt, then we can discuss more.
Sir,
Yeah.
sir, in reverse bias condition, the tunneling width is decreasing and the depletion region width is increasing.
No,
So
tunneling
how
width
can
is not decreasing. Nobody is saying that tunneling width is decreasing. It might be increasing a little slightly.
okay, sir.
Yeah, because this depletion width is increasing in reverse bias. But even after slightly increased depletion width, even then, if the tunneling possibility is there, in that case, this Zener breakdown takes place. So that's the point here. Okay. And that is the case in modern day micrometer when we have a few micrometer of n-type material in junction with few micrometer of p-type material. In that case, this depletion region is quite small and there might be tunneling. Although the most common form of breakdown in diodes is avalanche breakdown, where in high reverse bias, the electric field is so high that the carrier velocity is increased a lot, uh, and they may break the bonds of the material, and a lot of electrons and holes are generated in the depletion region, and the current increases a lot. And so that's the another kind of breakdown that can happen in the reverse bias. Yeah, so that is the another kind of breakdown that can happen, and the current will be almost the same actually, even in that case. That is known as the avalanche breakdown, and that breakdown might not be reversible actually. That might be irreversible as well. Irreversible means that it might sort of burn out the system. Okay. Now, is it this IV characteristics of diode? This part, if you have any question, let me know. Otherwise, this is more or less how the diode IV characteristics comes into picture. And let me rephrase here that the diode IV is a very interesting physics if we do it from the detail, because it involves diffusion, it involves drift, it has a thermal component as well because of the uh, carrier recombination generation. Okay, and since it is a semiconductor material, we need to take into account the Fermi level as well. So this IV expression or the current physics of the diode is quite interesting. It's not as simple as the metal resistor IV relationship. Okay. So let me, so there are two classes that I did not, could not take due to travel. And since this is the last week before the midsem, if required, I will take one class before the midsem and maybe I'll take one class after the midsem. And the class that I take before the midsem will be there in the midsem, might be there in the midsem exam. And the class that I would take after the midsem, the part covered in that will not be there in the midsem exam. Okay. Can I take, if, do you guys have a class right now or not? Hello?
No, sir.
Can we extend this class a little bit so that if you are not tired, although I don't want to torture you, so uh, let me know frankly.
We had regular three classes, so we are a bit tired, sir.
2 to 5 you had classes.
Yes, sir. And
Sir, we had a lot of
11 to 1 also, some of the batches had practicals.
Practicals. Okay. Anybody else? Yeah, was saying something. Can we have classes? So since this is mid-sem time, although I also don't prefer that, but can we have classes in the night so that you have a break and let's say 8 to 9 or 9 to 10, if that is feasible for you. If not, then we will not.
Yes, sir.
So the problem with the classes during the night is that we usually have some club induction or some meet icebreakers with some seniors or everything. That's the problem.
But that's also important, actually. That's also important. So in that case, let's maybe have the classes during the day. And although I wanted to cover a little bit more, but let me not do that now. And I'll get in touch with your CR and I'll have the class accordingly. Okay. Okay, then
Okay,
let's
sir.
yeah, close for the day. And thank you for your attention.
Sir,
Thank
just
you.
a question
Thank you.
about CMT.
Sorry?
Sir, I have a question about MT.
Yeah.
Sir, what kind of questions are preferred? Like, what kind of questions do you ask? Are they more based on reasoning or are they more theoretical or mathematical?
I would say reasoning and uh, a good or a good understanding of the basics that we discuss in the class. So
Okay, sir.
as you might have seen that we try to go to the basics of things and try to understand. So
Yes.
it's not, the exam is not going to be highly mathematical. Uh, all other courses might be mathematical because engineering exams are mostly mathematical, but this course is not going to be that mathematical, at least my part of the course. The second part, the communication part, might be more. So that is reasoning plus conceptual understanding of things.
So what is the duration of the exam?
Duration, I won't take it for more than 1 hour, actually.
Okay, sir.
Although, okay, yeah, let me clarify things by Wednesday because the exam schedule is also not. Have you received exam schedule by any chance?
No, sir.
No, sir.
No, sir.
Not yet.
Yeah. Once that is received, then maybe I would be able to let you know better. Okay.
Okay, sir.
Yeah. And don't worry. I would say that don't worry about this exam. It's not a big deal. This course is a small course. Okay. Okay, then see you soon. See you at least once before Friday because there are a lot of things to be covered actually. Although I won't hurry, don't worry that I would hurry and do so. You will not be loaded for the midterm. Okay, then yeah. Bye bye.
Okay, thank you, sir.
Bye, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.